No? All right. Good morning, everyone, and welcome to the second day of HVC 2012. Before we get started with our keynote of the day, I just want to remind those that have not yet registered to the social event, the excursion, this afternoon, please register shortly after the talk with Shirley at the registration desk. That's it. I'd like to have Henry here, our manager for the system engineering group here in IBM, present our keynote of the day.
Thanks, Amir. Okay, good morning, everybody. Hope you're all well rested and ready for another exciting day here at HVC. And I personally couldn't think of a better way to start this day. I'm proud to introduce our distinguished colleague, Professor Edward Lee, from University of California at Berkeley. Former chair of Computer Science and Electrical Engineering Department. Professor Lee current research interests center around design, modeling, and simulation of embedded real-time computational systems. He is a director of the Berkeley Center for Hybrid and Embedded Software Systems and is an IEEE fellow. He has co-authored 5 books and numerous papers, and has led the development of several very influential open source packages, notably Ptolemy. He has degrees from Yale, MIT, and UC Berkeley. Please welcome Professor Edward Lee.
Okay. Thanks, Henry. First of all, I'd like to just thank HVC for inviting me here. I have a lot of interactions and collaborations with people who specialize in verification. I'm not really a verification person, but I think that there's a lot of potential for very interesting applications of verification in the context of the sorts of systems that I'm interested in. And in particular, just to give you a little bit of context, the focus of my work these days is on what people today are calling cyber-physical systems. And the key idea with cyber-physical systems is that they integrate computing systems and networks with systems where there's absolutely non-trivial physical dynamics. So you can think of, for example, factory floor kinds of applications where you've got networked machines, each with their own controllers and each with their own control algorithms executing, but they have to orchestrate their actions across the network. And the scale of these systems, of course, can be huge. Power generation and distribution systems, for example, are a very nice and very challenging example of cyber-physical systems where there's a lot of dynamics in the engineering of these systems these days, because the fundamental structure of these systems is changing. Automotive systems are really good examples today as well, where a typical modern car has maybe 50 to 80 microprocessors in it, and they're networked and again orchestrating actions. And of course, there's a lot of risks associated with these, the transformations that are happening in these systems with increasingly open networks and so on. So, to me, this is a very exciting area and very dynamic. And I think that the big picture of why it's an interesting area from an intellectual perspective is that the engineering abstractions that have been in use for the last 200 years or so for the physical parts of these systems are very different from the engineering abstractions that we use for the computational parts of the system. In fact, in many ways, they're kind of fundamentally incompatible with one another. And so the big challenge in this area as an intellectual area is in trying to find a way to conjoin these engineering abstractions in ways that make sense. So this is really going to be the focus of my talk today, because I think that this is also where there's an opportunity for people who, in the verification world, in some ways, some of the most notable successes actually have been in the conjunction of physical processes with the logic of computing, because if you think about hardware verification, it really is rooted in both the computational abstractions and the properties of hardware, which are very much physically defined. In software, however, things get a little bit more challenging, because today, in the context of cyber-physical systems, computer programs do not adequately specify timing behavior, and timing behavior is an extremely important part of how software interacts with the physical world, right? When the software does something is really quite essential to how effective it's going to be. And a corollary for this is that if you're focusing your verification on the software, then you're not going to get a reasonable answer, right? Verifying the software as an engineering artifact doesn't actually tell you anything about the timing of the system, because the software doesn't actually express anything about the timing of the system. Now, you might say, well, the software doesn't express timing, and yet we write real-time software all the time. People write real-time software all the time. How is it that it doesn't express the timing of the system? Well, it doesn't. This is this collision of abstractions that I'm talking about. Okay, so let me give you the context. So in a typical cyber-physical system, here's a schematic of a very simple one, where you've got two computational platforms, a network fabric that they're using to communicate with one another, and they're interacting with a physical plant. So you might have actuators driven by one computational platform, sensors that are providing data to another computational platform. And we write software for these platforms. We might have a microcontroller in here that, there's a chunk of C code behind this. And this is a very small piece of C code written for an ARM embedded processor that is very simply trying to start up a program and then run some operation for 2 seconds and then switch to some other operation, okay? And the way that it's doing this is it's initializing an external device, a timer, by writing to a memory mapped register to set up an interrupt request, okay? And then it's got an interrupt service routine that it's using to count ticks of this timer, and then the body of a while loop here is going to just execute until the timer expires, okay? So you think of this as the program as an engineering artifact. Does this in fact specify the timing behavior of this system as an engineering artifact? And the fact is, it doesn't, right? As an engineering artifact, this is a program in C. C has a semantics, and the C semantics actually says very little about the behavior of this system. In fact, under the C semantics, this is actually a rather weird program, because nowhere in the body of main does this routine get called. Okay, so in principle, a compiler could actually optimize this away within the semantics of C. The interrupt service routine doesn't get called by the program, therefore, within the semantics of the program, it's unnecessary, it doesn't need to be carried. So you have to put extra annotations to tell the compiler, please don't do that, okay? So how is it then that we have specified that we have a piece of code that should run for 2 seconds? Well, in fact, the fact that it runs for 2 seconds, if it does, which we actually have very little assurance that it will, is a consequence not of this program at all, but rather the conjunction of this program and the hardware on which it runs. All right? So when you map this hardware onto a particular board, this is a board that happens to have an ARM processor on it that can run this program, okay? So this might be controlling a robot somewhere. And in fact, the behavior of this program will be dependent on every detail of the design of this board, okay? It's dependent on the specifics of the hardware that's attached to the processor that implements this timer. It's dependent on the clock that is associated with that's driving this timer, or your choice of crystal oscillator. It's dependent on the memory architecture of this board. It's not even enough to know that this is an ARM processor, right? So, I mean, IBM 50 years ago invented the concept of an instruction set architecture to provide a layer of abstraction so that programmers didn't have to rewrite the code every time there was a new version of the IBM 360, right? That, unfortunately, it's not enough to know what the instruction set architecture is here, to know what the timing behavior of this program is. You have to know, in fact, what hardware, down to the silicon and wires, it's going to run on in order to be able to understand what the timing behavior of the program is. So as an engineering artifact, is it useful to verify this program? Well, maybe for things other than timing. But for timing, no, it's not actually useful. It's not telling you anything in any sense that would be satisfactory to a verification person. So when precise control over timing is needed, the designs end up being brittle because they're so dependent on the details of the hardware. Okay, small changes in the hardware, the software, or the environment in which they run can cause big unexpected changes in timing. And every time you make one of these small changes, you have to redo all of your testing. So you cannot, for example, if you're a car manufacturer, decide to buy a cheaper version of an arm with a new technology. It's clocked much faster, it's got better performance, it consumes less power, all of that. You cannot just buy that and expect it to behave the same way. In fact, if you replace that ARM processor, your older ARM processor with that new one, you've got to retest your system completely, everything, okay? This has a lot of consequences in the design of cyber-physical systems. So I flew over on a Boeing 777, which is Boeing's first fly-by-wire aircraft, okay? Boeing started manufacturing the 777 in 1995. And they're still producing them and still selling them, and they're still manufacturing them. And they actually expect to manufacture a plane in a product line like that for approximately 50 years. They plan for a 50-year production run of the aircraft. During that entire 50 years, they will not change the microprocessors they use. So if they make a Boeing 77 in the year 2030, it will include microprocessors that were made in the early 1990s. Boeing had to stockpile these microprocessors, right? They've got they have a liquid nitrogen cooled storage facility to store the microprocessors that they're going to use to make the airplane. And if they run out of microprocessors, they stop making the plane, okay? Because it's too expensive to revalidate the whole design with a new piece of hardware. It's simply too expensive. You can't expect the same behavior when you replace the hardware. This is ridiculous. In fact, to me, this ought to be a profound embarrassment to computer science. Okay, the fact that they end up having to do this. And if you talk to people in the business, car manufacturers don't have quite such a bad problem. They don't make cars for 50 years, right? So they go obsolete much more quickly, but they still stockpile the parts, because if the vendor of the parts decides to change their production line and change the process they're using to use a smaller feature size, they're going to get different behavior from the same microprocessor. And they end up having to redo all of the testing. So they stockpile the parts as well. So this is really a problem for people. So it means that manufacturers can't take advantage of improvements in hardware, for example, to reduce weight and power. And it means that designs end up having to be over-provisioned because, one of the consequences of this is, in the design process, since the timing behavior of the system emerges from the hardware implementation, right? If you make the wrong choice of hardware early in the design process, you get into big trouble late in the design process, right? Because many of your pieces of your design have gotten validated on this particular piece of hardware, and all of a sudden you find you're under-provisioned. And if you have to replace the hardware with more capable hardware, you end up having to go back and redesign everything. So as a consequence, you make very conservative decisions up front. You choose microprocessors that are way more capable than what you actually need. And you configure them with way more memory than you actually need. And then, at the end of your production run, you hope that you, in fact, had allowed enough margin there. So we end up with over-provisioned designs that consume more energy than they need, way more than they need, and cost more than they need. Now, I'd like to talk about how we're going to solve this problem. And I'd like to acknowledge Herman Kopetz, with whom I had breakfast with at a conference, at an MSoft conference, this was probably about 8 years ago. And he just made a comment at breakfast that changed my thinking about things, because I had never really thought about things this way. And so now I call this the Kopetz principle now, because I learned it from him. And to many of you in the verification world, probably, it's obvious, but it wasn't obvious to me. So what he said over breakfast, and I wish I had recorded it because I didn't, but I have to paraphrase it. So he essentially said that many of the predictive properties that we assert about systems, so for example, determinism, timeliness, reliability, are not in fact properties of the implemented system at all, but they're properties of the model of a system. Okay? So we can make definitive statements about models. We can assert, for example, that a program is deterministic. Okay? But an implementation of a program, barring philosophical or religious arguments, isn't deterministic, right? How does the program behave when the microprocessor is being crushed? Well, it's going to behave non-deterministically, right? So in the physical system, you can't really make definitive statements. So verification, where you do proofs, okay, the proofs are not proofs about a physical system, they're proofs about models of the physical system. And proofs about models, the validity and the usefulness in these proofs depends on the model fidelity, which is always an approximate, okay? Model fidelity means how well does your model fit, how well does it represent the physical system being modeled, okay? So I call this the copet's principle because it really changed my thinking, but I've subsequently discovered that, this is really not such a new thing. So Solomon Gulam wrote this wonderful book way back in 1960s, and one of the things he had in there was a diatribe about making sure that you could understand the difference between models and the system being modeled. And he used this expression that I just love: you will never strike oil by drilling through the map, okay? So you got to understand the difference between the model and the system being modeled. Now, I want to emphasize that although you will not strike oil by drilling through the map, in no way does this diminish the value of a map. Okay? Maps are still extremely useful. And in fact, in the verification community, it's all about maps. We're always verifying maps. We're never verifying physical topologies, right? So verification wouldn't exist as a field if we didn't have some value for maps, right? So in the context of cyber-physical systems, timing is not part of software semantics. The notion of a correct execution of a program in C, which is the most widely used language for embedded systems, C#, Java, Haskell, OCaml, any of these languages, even Ada, which has nominally some timing behavior integrated into the language, okay? It's still true that correct execution of these programs has nothing to do with how long it takes to do anything. The notion of correctness does not include timing, okay? And nearly all of our computation and networking abstractions are actually built on this premise. So as a consequence, when programmers need to specify timing behavior, they have to step outside the programming abstractions to specify the timing behavior. So in the case of that little snippet of C code that I showed earlier, you have to write to a memory mapped register. From the perspective of C, all you've done is written to a memory location. On that particular processor, if you read back from the same memory location, all the bits will be flipped. Okay? So from the perspective of C, you don't even have a good memory model, right, in this hardware, but you have to, in any case, you have to step outside the programming abstractions to specify timing behavior. As a consequence, programmers have no map, okay? In the context of timing, there's no map. You're just, you're going to have to do your drilling for oil without a map, okay? And that's what people do. And that's what people have done for many years in building embedded systems. Now, it's not that computer science has ignored timing. In fact, if you look at the first edition of Hennessy and Patterson, which had a big impact on the field of computer architecture, and the key thing was there was just driving home that performance metrics should be the dominant criterion for design. Okay, so performance is about timing, naturally. But performance is a quality criterion. It's not a correctness criterion. Okay? And there's a big difference between a quality criterion and a correctness criterion. So performance is not the same thing as achieving timing behavior. Very, very different, okay? So the question that I raise is, can we make timing in software a correctness criterion, not a performance criterion? Now, in verification, of course, you're used to correctness criteria, right? And we have a notion of correct execution of a program. And if you have a snippet of code, you can apply analysis techniques. For example, for this little chunk of C code, I can assert that line 8 will never execute. Okay? Now, in fact, C is kind of a messy language. As maps go, it's probably the Apple version. Okay? So C has its problems, right? In fact, if we want to really assert that line 8 never executes, then we have to ensure that there's no other thread executing, or that there's no interrupt service routine that can overwrite the stack. Okay, but in some modern languages, these things are assured by construction, and so we have slightly better maps. But the issue is that if you have a pretty good map, meaning that there's a good strong semantics to this program, you can actually develop absolute confidence in the software, where what you mean by absolute confidence is that line 8 never executes. Absolute confidence? Can we ever have absolute confidence? Well, again, distinguish the model from the system being modeled. For models, we can have absolute confidence. Okay? We can make very definitive assertions. Line 8 never executes. That's absolute confidence. Okay? Does that mean that line 8 will never execute in a physical realization of this? No. I mean, an alpha particle might change a bit in the program counter and we'll start executing line 8. Okay? A physical system you never can have absolute confidence in, but that doesn't diminish the value of having this map and then being able to make assertions about the program. But we can't do that with timing. Okay? Now, the technology on which we build these systems, however, is actually very good at timing. It's extremely good at timing. Okay? We can build a synchronous digital circuit that'll perform a logic or arithmetic function with extremely precise timing, with extremely high reliability, do this operation 1 billion times a second, and run correctly for years. Okay? We have the technology to do that. But we've chosen, in the abstractions that we've overlaid on this, to discard that timing precision that the underlying technology is capable of. We don't bring that to the designer. We hide it from the designer. Okay? Now, in networks, we have the same issue. Networks are also, they're built on physical devices, and, wires are actually, in the aggregate, pretty deterministic. And so it's possible to build networks that are capable of pretty precise, well-controlled timing behavior. But again, we've put layers of abstraction on top of that underlying hardware, where timing emerges from the details of the implementation rather than from some kind of thing that you could design in. So even in, today there's a lot of movement towards, quality of service aware networks, like, for example, AVB, which is a variant of Ethernet that gives you really pretty precise control over timing behavior. But the fact is that the timing behavior is still going to emerge from the packet priorities and the network topology. And so it emerges from the physical implementation instead of being designed into the system. Okay? Now, consequences. Okay, verification asserts properties of models, not of real systems. Verification can only assert properties that are expressed in the modeling semantics. That's all you've got, right? And if the model says nothing about timing, then timing properties cannot be verified. So we could just say, all right, we're done. So HVC, sorry guys, just keep doing what you're doing, but just don't talk about timing. Okay? But I'm not going to accept that, because I think the stuff that you guys are doing is too useful and too powerful, and we got to find a way to make it talk about timing. Okay? So how are we going to do that? We could say, all right, well, let's apply these wonderful tools that you've got to doing program analysis, and then we'll just do execution time analysis on programs. Find the worst case execution time of a chunk of code. Okay, so what do you have to do to find the worst case execution time of a chunk of code? Well, you have to analyze the paths through the program. Okay, this is already an undecidable problem. Okay, it's hard, right? So, but we're not scared by hard problems. We like hard problems, right? So we'll do that. But unfortunately, it's not enough to solve this undecidable problem. It's not nearly enough to solve this undecidable problem. Okay, in addition to solving this undecidable problem, you have to have a detailed model of the microarchitecture. You have to know every detail, right? Not what the instruction set architecture is, okay, but how the designer of the silicon chose to realize that, that instruction set architecture. You need to know that. You need to know every detail of the memory system. You've got to know exactly how much memory is in cache. You have to know exactly what the cache replacement policy is. If you've got a multi-core architecture, you've got to know what all of the interaction mechanisms are across cores. Extremely difficult problems, okay? Moreover, even with all of that knowledge, you have to make a bunch of assumptions that are actually rarely satisfied in the field. You've got to assume complete knowledge of the execution context of this program. You've got to put many constraints on preemption and concurrency. If you say, one of the things you have to say to do worst case execution time analysis is that interrupts don't occur. Well, in the design of the control system for the 777, interrupts don't occur because the FAA doesn't allow them to use interrupts, okay? A 40, 50-year-old technology for, and the state of the art in I/O, and they're not allowed to use it. Again, an embarrassment for computer science. They can't use much of the technology that computer scientists have provided because it creates all kinds of problems. So execution time analysis can tell you something about what a program does on a particular piece of silicon. That's all. Again, it's working without a map. And it's an extremely difficult analysis, and you do this analysis, and if anything changes, or any of your assumptions were wrong, then the analysis isn't really very valuable. So, our first goal is let's reduce this problem to just the first one. Okay? That's already hard enough, and if we can just solve that first problem and not have to worry about all of these, we'd be in great shape. So how are we going to do that? Well, so we have a project where our goal has been to try to show the world of computer architecture that you actually can put semantics, timing semantics, into instruction set architectures, okay? And moreover, that you can do this without, what computer architects will say, oh, no, please don't tell me that because we're going to have to give up huge amounts of performance. Baloney. That, it's dogma that you're going to give up huge amounts of performance in order to gain control over timing. I think it's the reason that computer architects have used techniques that give up control over timing is because timing is irrelevant to correctness. And those have been the easiest techniques for getting performance. The easiest techniques are ones that trade performance for timing variability, and you end up with little or no control over timing and excellent performance. Our goal in this project was to demonstrate that you can get excellent performance and still have control over timing, okay? So we call this the Pratt project, Pratt is a nice acronym because it has at least 5 different meanings. It stands for precision time processors, or predictable repeatable timing, or performance with repeatable timing. The fourth meaning is it's the French word for ready. I like that. And it's the Dutch word for fun. So those are all nice meanings. So the approach that we're taking in this project is, first of all, rethink this notion of an instruction set architecture, right? I mean, the concept of an instruction set architecture introduced by IBM with the IBM 360 family in the 1960s really hasn't changed since then. The things we express in an instruction set architecture today are the same things that IBM chose to express in 1962. Okay, a lot of things have changed since 1962, however. Maybe it's time to re-examine this a little bit and see, well, maybe we could put some slightly different things into the notion of an instruction set architecture. It's a layer of abstraction. It's a mapping technology, okay? Maybe we should think about changing that mapping technology a little bit. Now, we have to do this in such a way that we get the benefits of that mapping technology. So an instruction set architecture, one of the goals of an instruction set architecture is to insulate the designer of software from the designer of hardware, right? The idea is, the software guy says, oh, well, those hardware guys, they're evil, right? They're going to do all kinds of sneaky tricks and they're going to break my program. And the idea of an instruction set architecture is to get that insulation so that the program still works. Now, when this was developed for the IBM 360 family, it was about your payroll program still working, okay, when you upgraded your processor. So you had to be able to run your payroll program. But we're not focused on payroll programs anymore these days. And in the context of cyber-physical systems, the software is doing very different things than payroll programs, right? They're really not like that. those payroll programs, right? But we still have to get that insulation. So in particular, we need to allow for multiple realizations and for efficient realizations of an instruction set architecture, okay? So how do we do that? Well, let me first give you a sense of what I think the things we want at the programming level of abstraction, at a minimum, right? We want to be able to gain some control over timing. So we'd like to be able to, for example, specify that a code block should not take more than 500 milliseconds to execute, right? Now, we might want, since, there's an arbitrary piece of code in here, and it's an undecidable problem to determine paths through the program, right? So we might want mechanisms for handling exception conditions where we could, execute some panic routine if in fact it takes more than 500 milliseconds, okay? So you can write code like this today in C, and it's exceedingly tricky, okay? So here's a mechanism. So suppose that we really want to, run this for 500 milliseconds, and if we overrun that 500 milliseconds, we want to immediately handle the exception, right? Because we've reached some safety critical concern. So in C, the way you would do this today is using a set jump and long jump mechanism, okay? So the way that this works is you start with an if statement. If not set jump, okay? Now it turns out that under the semantics of set jump, this will always return false. So this not set jump will always be true. So if true, we execute this code, okay? And in this code, we talk to external hardware, again, step outside of the programming abstraction to talk to a timer to set up an interrupt that will occur when that amount of time expires, okay? Then we start executing our code block. If we reach the end of the code block before that timer expires, we deactivate the exception and we're done, okay? If, on the other hand, while we're executing the code block, the timer expires, then we execute an exception handler which executes a long jump. Now what long jump does is it unravels the stack to the point where set jump was called, and set jump now returns true, okay? So what happens is if not set jump is false, therefore we now execute the panic routine. So, and we never return from interrupt in this, okay? So we don't resume executing this code. Now this is pretty nasty because if you do anything in this code that operates on data structures, which most interesting code does, those data structures may now be completely corrupted. You can't assume they're in any coherent state. In fact, the only data structure that you can assume is still intact is your stack. Everything else is messed up, right? So the only thing you've done is preserve the stack, which means you don't have to hit the reset button, okay? But unless you're a very disciplined programmer, you're almost starting over again, right? This kind of code is very difficult to analyze, very difficult to make robust, really nasty, actually. So, but really, it's not the code that we want anyway, right? What we'd really like to do is be able to prove that panic never executes, okay? So here's a kind of a taxonomy of timing constructs that we could use that are related to this. So this one that I just described is what I call the version 3, or immediate misdetection. Okay, so that means as soon as the time expires, we execute the panic routine. You could also do late misdetection, which means you let the code block execute to completion, and then you handle the exception condition. And that at least means your data structures are still intact, okay? And for some applications, that's fine. You could also do just kind of a best effort thing where you say, well, I'll execute the code to completion, but if I finish early, I'll pad the code, right? So that it actually takes 500 milliseconds. And then, as long as I always finish early, then at least I get repeatable timing, okay? The fourth version of this, however, is really the most interesting one, okay? This is the one that we call MTFD, okay? And that's where we have a code block, and we're going to say, I would like to execute this code block in the specified amount of time, period. No excuses. Just do it, okay? It's a correctness criterion. Your only excuse for not executing this code in this amount of time is a hardware failure. Okay? We're used to correctness criteria like that in programming, right? And again, we're talking about a map now, not about the physical system. The physical system could violate this, right? But it would be an incorrect execution. And the only excuse for an incorrect execution is going to be a hardware failure. So MTFD stands for meet the final deadline. Just do it. Okay? No excuses. How can we do that? Can we provide architectures that would enable an MTFD block? Okay? We can, actually, but there's a lot of challenges. And in fact, if you work in computer architecture, I would think this would be wonderful because, a lot of the people who work in computer architecture these days are enormously relieved about the emergence of multi-core because they were starting to get bored, right? There wasn't anything to do in computer architecture. Intel was doing everything, and multi-core at least has opened up some possibilities for them to do interesting things, right? So that's a tremendous relief. But this opens up everything else. All the stuff that no one was working on anymore because Intel had taken over, right? You can start to think about pipeline architectures again. You can start to think about memory hierarchy again. You can start to think about I/O mechanisms again. All kinds of things you can do, right? So, in fact, you have to rethink all of these things because the fact is that all of the technology that we've developed for the last 40 years in these areas has been about improving performance without any regard to controlling timing, right? So timing is irrelevant as a correctness criterion, it's just a performance criterion. So we've actually built a Pratt machine that is an implementation of an ARM instruction set, and we've got it implemented in the form of a soft core that we can synthesize to an FPGA. So it's a full-blown implementation of an ARM, and it's a Pratt machine with perfectly repeatable timing. And we're able to compare it against other implementations of the same generation of ARM processors. Okay, so this is the useful thing because we can do performance analysis on this to understand what the costs of getting this precision time architecture. Now, we have solutions for each of these pieces of hardware challenges that I've described, pipelining, memory architecture, and so on. And the key thing is that we're not, in fact, trying to just say, well, let's just give up on all the performance. And we could make a Pratt machine by not doing any pipelining, not having any cache, etc. But that's not going to give us acceptable performance these days. So we need to have these things. So the way we deal with pipelining is an old technique, which is we interleave a pipeline with a multiple set of registers. So we have a multiplicity of hardware threads, and each hardware thread is running more slowly than the clock rate. Okay. And it sees no pipeline effects. So there's no issue of interaction across instructions in this pipeline. This is an old technique. In fact, it was used way back in the 60s in the CDC 6600 in the peripheral processor, which was used for controlling drum memories. Okay, drum memories are actually cyber-physical systems. You have to control the timing pretty precisely. And one of the advantages of this architecture is that you can control the timing pretty precisely. Okay, so you have a multiplicity of hardware threads. We do have a memory hierarchy. We use a scratch pad rather than a cache. Now, what's the difference between a scratch pad and a cache? Well, from the hardware perspective, a scratch pad is simpler because the replacement policy is implemented by software rather than by hardware. So you don't need all that hardware to implement the replacement policy. Now, the advantage of having a replacement policy that's implemented in software is that the replacement policy can be tuned to the program. Okay? This actually gives potential for enormous performance improvements, okay? So today, if you have a real-time program that has most real-time applications have some mixture of timing critical pieces and non-timing critical pieces, right? So the typical thing you do is you just give highest priority to the timing critical things. So the operating system will always give preference to the timing critical things. And whenever your timing critical thing executes, it will evict everything you've got in cache, okay, because it's going to execute and it's going to need the cache, and the replacement policy is implemented in the hardware, and you have no control over that anyway. So as soon as you're accessing memory, you're going to end up evicting everything in cache. Well, maybe you didn't need that. I mean, suppose your timing critical thing is running at a fairly slow periodic rate, okay? If you had a timing specification in the program, you might discover that in fact your timing critical thing never needed to use the cache at all. Okay, it would be perfectly happy using the DRAM, and it would still meet its deadlines. Okay, moreover, it didn't need to have the highest priority. It just needed to execute at the right time. And if it executes at the right time without using the cache, that actually improves the performance of your non-timing critical programs, which are maybe performance sensitive. They're the ones that are going to affect the user's quality of life, right? How quickly they get a response on the GUI. Okay, so you could actually improve the performance of those things while very reliably meeting your real-time deadlines. Performance improvements that are possible because you gain control over timing. Okay, so this idea that you must sacrifice performance to gain control over timing is nonsense. Okay, now of course there's lots of work for computer scientists in lots of dimensions here, right? I mean, who's going to do the software policies for managing the scratchpad? Well, that's going to be the compiler people. Those guys haven't been quite as bored as the architecture people. They've got work to do, but you know, they're working on 3%, 5% improvements in compiler performance. This is a very different kind of thing, right? This is actually working with a different mapping technology, which to me is much more intellectually interesting. Performance cost? Well, with caveats, no. Okay? In particular, my PhD student, Isaac Liu, did a bunch of experiments on a set of standard benchmarks where he compared this PT ARM against a conventional ARM processor with a similar sized pipeline, similar memory architecture, and the precision-timed ARM beat every one of the benchmarks in performance, okay? With the caveat that he assumed that there was enough concurrency to keep all the hardware threads busy. So in effect, what he was comparing, if you had 4 hardware threads, he would compare 4 runs of the benchmark on the PT ARM against 4 runs of the benchmark on the conventional ARM. And maybe an unfair comparison, but we beat the performance of the benchmarks every time on those 4 runs. On one run, we didn't. The single thread performance was not as good. But the aggregate performance, if you have enough concurrency, was consistently better. And this was implemented in the same technology, clocked at the same rate, okay? But actually, our pipeline is simpler, our memory is simpler because we don't have all of that cache replacement hardware. This processor can be clocked at a higher rate, so we can actually get better performance from the hardware as well, which we didn't factor into these measurements. So this is just better performance that we're getting simply because we're not suffering the effects of pipeline bubbles and things like that. So this canon, this dogma that you have to give up performance in order to gain control over timing, don't believe it. It's not true. So the next step, of course, this is one particular implementation of an architecture. We need to have the ability to have a variety of implementations. So for example, if I have a code block with an MTFD, how can I be sure that if I get a new version of the processor, it's still going to execute correctly? Okay? Now, notice here we have actually a tremendous potential advantage, right? If the program has all of its timing critical operations specified using code blocks like this, I can do late binding to the hardware, right? As long as I can guarantee that MTFD is respected by a piece of hardware, I can replace the hardware. I can replace it at the last stage of design. Once I've got my program all worked out, all debugged, ready to ship, I can now pick the processor that meets all my MTFD deadlines, consumes the least power, is the cheapest to manufacture, okay? At the last stage of design, instead of what people do today, which is to pick that processor at the first stage of design, where first of all, we've now gained 2 years of Moore's Law advantage because we're picking the processor 2 years later, right? Moreover, we're going to pick the processor. We're not going to over-provision this thing. It's going to be the processor that exactly meets our specification. Huge potential advantages in performance, power consumption, etc. So how do we do that? Okay, well, we have to rethink a little bit the tool chain. So the way to implement this MTFD, we've got some source code. It's got code blocks like this in here. The compiler will produce object code that has these MTFD instructions in it, and then we run it through an analyzer. This is you guys' job. Okay, here's where you solve the undecidable problem. Okay, you look at the code block in here, you analyze it. You may decide, I can't bound it. It's an undecidable problem. Come on. Okay. So if you decide you can't bound it, you reject the program. And because it's an undecidable problem, no matter how good your analyzer is, you will reject some valid programs, right? That's what it means to solve an undecidable problem. So every analyzer will reject some valid programs. But if you get one where you can bound the paths through the program, what you produce is not just a yes or no answer, but rather a formula, a predicate. Okay, a Boolean valued formula that is a function of the architecture parameters. So it has as inputs a clock rate. So your clock rate has to reach a certain threshold. You have to have a certain amount of scratch pad memory. You've got to have a certain, details about the architecture are expressed in these architectural parameters. Your analyzer produces a predicate, and then before you link and load this program, you check the predicate against the particular specification of that particular piece of silicon. Okay, this piece of silicon is going to be clocked at this rate, and therefore either the checker will say, well, MTFD is either respected or not, and if it is respected, then you can link and load it, and now you get out of the end of this absolute confidence software. Okay? So that changes the tool chain a little bit. Now, programmers are used to compilers rejecting their program. They're not used to linker loaders rejecting their program. Okay? So this is going to change that tool chain a little bit, but I think we can live with that. Okay? Now, the second question, which I think is interesting, is how do you get this source code? So in particular, I actually don't like the idea of having application programmers, the guys who are the automotive engineers, writing code blocks with MTFD. Okay? I don't think it's the right level of abstraction for gaining control over timing. And so we have a second project that's focused on how to get this source code. Okay, and I'd like to just briefly give you a sense of what this project is, but I can't. I don't want to go into too much detail because I will really try your patience. Okay, so today there's a lot of interest in the embedded software community in generating programs from models. Okay. So these can be Simulink models, for example, are widely used in the automotive world. You build a Simulink model, you generate a program, and SCADE is used in avionics. Airbus uses it to synthesize some of the safety critical code that's used in the control systems of Airbus aircraft. These are pretty high level models, and you synthesize programs from it, okay? And so that's going to be the general approach. The way we're going to get this software is we're going to build models in some modeling environment that has time as a first-class citizen in this modeling environment. And then we synthesize programs that have MTFD instructions in them that assure that these things are realized. Okay? Now, there's a few challenges. In cyber-physical systems, we need to have a temporal semantics that is actually going to have to stretch over networks. Okay? Because it's not enough on a factory floor, for example, to meet deadlines on the controller of a single robot. If these robots are orchestrating their actions, like you saw in the video on my second slide, you need some timing coordination across networks. That makes the problem even more interesting, right? So the programming models are going to have to be able to embrace a somehow distributed notion of time. And now we have a little bit of a problem because controlling timing in distributed systems can be pretty challenging. Now, fortunately, there's a lot of activity right now in the networking world on synchronizing clocks across networks at high precision. Now, you may or may not be aware of this activity, but I think it's really kind of a game-changing thing that's happening right now. Okay? The question that we're addressing is that if you assume that you can synchronize clocks on computational platforms across a network, how would that change how you design distributed real-time software? Okay? And we think it changes things pretty dramatically. Now, I don't want to give this too much hype, but I actually believe that we're in the midst of a phase change here that is big in what's happening in time synchronization. And I put it in the context, I make this sort of bit of hyperbole statement. Time synchronization is going to change the world again. Okay? It's done it before. In the 1500s, the Gregorian calendar synchronized clocks around the globe to plus or minus 1 day. Okay? In the 1800s, the railroads synchronized clocks, maybe not around the world because railroads don't traverse oceans very well, but across continents to within seconds. Okay? And there were huge advantages to doing that, to synchronizing those clocks. What's happening now is we're synchronizing clocks to within nanoseconds around the world. Okay? And this is good. In 5 years, I predict anything that's on a network, which will be a lot of things, will have a synchronized clock with everything else on the network, and these things will agree on the current time of day to within a few nanoseconds. Okay? This is pretty game-changing, right? And if you think about the implications that that has on how you design software that's orchestrating things across a network, you can do a lot of things that leverage that notion of time synchronization that you can't do today. So, by analogy, in the railroads, right, before they had well-synchronized clocks, the way things worked, well, before they had, good clocks at all, the conductor would, the engineer would look down the track and see if there was a train coming, and if not, you could go, well, that's obviously not a good technique. So they used pocket watches, right, that were synchronized, and if you had errors in pocket watches, you got collisions on railroads, right? Today in our networks, we put up with these collisions every day, right? They're happening all the time in our networks, these collisions, and I don't think they're necessary, really. And I think if we synchronize clocks, we can make our networks much more deterministic, much more reliable. So you could make Skype actually work rather than you're right. Okay, you've all heard that, right? All right. Now, so time synchronization is really happening. So in particular, anyone who makes a PHY chip these days, which is the hardware that interfaces to the Ethernet, pretty much all of them are putting in what it turns out to be a very modest amount of hardware to support a standard called IEEE 1588, which was the first version of this standard was established in 2002, second version in 2008, and it's getting widely deployed. Okay, so pretty soon, any Ethernet PHY chip will have hardware support for IEEE 1588. And this is able to synchronize clocks on local area networks to within a few nanoseconds. Okay, and it does it just by exchanging information using TCP/IP packets. Okay, so it overlays on top of TCP/IP, and you synchronize your clocks, and the clocks on this network will agree on the current time of day to within a few nanoseconds. Okay? How does this get used? Well, here's an interesting product. This is made by Bosch Rexroth. This is a printing press. This is a machine that occupies a room about this size, maybe a bit bigger. It's got hundreds of microprocessors on it. These yellow cables are all Ethernet cables. It's got quite a few routers and switches in it. Okay? And the actions here are orchestrating. There's paper flying through this machine at about 100 kilometers an hour. There's inkjet nozzles that are depositing ink on this paper as it's flying by with precisions of a few, very small precisions. And there's, of course, a lot of fault tolerance code. Paper is kind of a nasty medium. It can tear, right? And you have to orchestrate shutdowns of this thing if you get faults in the paper. You can't just cut power to all the motors or you get a freeway pileup, okay? So orchestrating the timing across this network becomes extremely critical. They're using Ethernet and TCP/IP for the communication here. That's crazy. Nobody in the industrial automation world does that until now, okay? By leveraging this time synchronization, they actually never lose a packet. Again, we're talking about a map. Of course you could lose a packet, right? But in fact, the way that they've designed this software, if it's executing correctly, they never lose a packet. So the latency of a packet delivery is bounded and deterministic, okay, in this system. They can truly orchestrate actions across a network. Now, of course, this isn't an open network. You can't SSH into one of these microprocessors, or things would get a little more complex. But so we still have some software challenges to enable these networks to become more open. But nonetheless, this is an existence proof that we can actually gain control of this networking technology across distributed systems. Now, my favorite example of time synchronization is what they're doing at CERN in the Large Hadron Collider. So the Large Hadron Collider is a ring. This is a picture of the inside of it while it was being constructed. Right? It's a particle accelerator. It's 27 kilometers around, and it straddles the border of France and Switzerland. So it crosses the border twice. So it's about 10 kilometers in diameter. Okay? And CERN has developed a clock synchronization technology that combines this IEEE 1588 protocol with another technology that was actually developed originally by internet service providers like Comcast and so on in order to improve the reliability of video delivery and telephone service to your home over TCP/IP. Okay, so they combine these two technologies, and they can synchronize a clock here with a clock 10 kilometers away to within 80 picoseconds. So the two clocks will agree on the current time of day to within a precision of about 80 picoseconds. 80 picoseconds at the speed of light is about this far. Okay, that's extraordinary. That essentially crystallizes your notion of time. Okay, this technology they used. You may remember early last summer, CERN announced that they had measured neutrinos traveling faster than the speed of light. I talked to the graduate student who found the problem with the experiment, and the way that he found the problem was using this White Rabbit clock synchronization technology. That's how he identified the problem, by being able to synchronize clocks, in this case, not 10 kilometers apart. These were 170 kilometers apart. One of those clocks was embedded way down inside a mountain because you have to, neutrino detectors have to be surrounded by large amounts of rock. So he used this technology in order to be able to find the flaw in the experiment and revalidate Einstein and show that, in fact, neutrinos did not go faster than the speed of light. Okay. In wireless networks, this is also happening. Clocks are getting synchronized in wireless networks. Now, you might think that, oh gosh, that must be much, much harder. Well, it is a little bit harder, but it's actually not much, much harder. And there's huge advantages to doing it in wireless networks. So if you have an ad hoc network of a bunch of battery-powered wireless sensor networks, and you'd like these things to communicate, well, when should they communicate? Well, the brute force technique is you put a radio on them and they listen all the time, right? They listen for incoming packets. And the battery lasts about 3 weeks, okay? And then you have to go and replace the battery on these systems. Well, that's not going to work, right? You need batteries to last 5 years, 10 years, okay? So the way that they're using clock synchronization is they synchronize the clocks on these networks, and the processors wake up at the time when they expect to receive a message. And if they get a message at that point, great. If they don't, they go back to sleep. And then they will typically communicate when they wake up because they use the communication to synchronize the clocks. So they correct any errors that have happened as a consequence of the clock drifting, and then they go back to sleep. And you can extend the battery lives of these things from literally weeks to literally years just by using that technology and waking up these things periodically and leveraging clock synchronization to wake them up. What about security? Well, it seems like clock synchronization would open up, a Pandora's box for security people to attack you, right? They could mess with your clock synchronization. Turns out, actually, clock synchronization has much more potential for enhancing security than risks for degrading it. And the reason is that you can make arbitrarily stable clocks. So you can have clocks that will run for a rather long time and still remain synchronized with other clocks with whom you are not communicating. Okay? If you're willing to spend enough money, you could buy one of these clocks. But that's several $1 million. But this clock drifts fractions of a nanosecond over years, right? So you can get very little drift, but for much more modest amounts of money, you can control the drift of clocks, and that enables a whole bunch of things. One of them is you can use it to prevent packet losses. You can detect hardware failures. You can detect denial of service. So, denial of service is fundamentally a disruption of timing. If you have no temporal semantics, how do you decide when a disruption of timing has occurred? Well, today you decided, well, my customers are getting frustrated. My website response is too slow. People are starting to call me on the phone and complain, right? No semantic basis for deciding that a denial of service attack has occurred. If you have a temporal semantics in the network, you can decide immediately, there's a violation of my assumptions here, okay? Let me block off that violation, right? So it enables security techniques that were not enabled before. You can detect GPF spoofing and the precision time protocol spoofing. So I learned recently that it's very easy to record a GPS signal today and play it back tomorrow. So I could mess with you guys' phones, right, and make them think that they're in California yesterday, right? It's easy, okay? It's easy to do. And so how would you detect that? Well, it turns out if you have clock synchronization, it's pretty easy to detect that it's not yesterday, actually. I have a stable clock that tells me, no, time doesn't jump by 24 hours suddenly. Therefore, I can detect that spoofing, okay? Again, a security enhancement, not a security degradation. Okay, so how are we taking advantage of this? Well, we're building a programming model for distributed systems that is leveraging this concept of time synchronization. So the idea is that you've got a computational platform, some microprocessor. It's got sensors that are interacting with the physical plant. It's communicating over a network fabric to other programs that are executing somewhere else that have actuators that are also interacting with the physical plant. And we're trying to get control over the overall closed loop dynamics of this system. We leverage time synchronization. The first thing we do is we introduce into this programming model a semantic notion of time using timestamps. So the idea is that the communication that occurs across the network is via time-stamped messages, and the clock synchronization gives these time-stamped messages a global semantics, right? It's not perfect. Clock synchronization isn't perfect, so you have to introduce some assumptions and some margin, but you can do that. So we bind timestamps to real time at the sensors and actuators, and that gives us some meaning there, and it's possible then to get deterministic behavior across distributed systems. Deterministic behavior with respect to a model, not a physical system. This model makes certain assumptions. It assumes bounded time synchronization error. Interestingly enough, our technique can detect violations of this bounded time synchronization error when they matter, okay? We assume bounded network latency. Again, we can detect violations of this assumption when it matters. And we can achieve determinate distributed computation. So we call this model TIDES. It's got a silent P in the front, and that's would take me much more time to specify it in full detail. But one thing that I think, one property of this model that would be of interest, I think, to HVC people, and we'd love to get some interaction here, is the schedulability analysis problem. So in particular, these models actually specify in the model the latency between a sensor and an actuator. So we specify how much time should elapse between taking a measurement of the physical world and producing some response on some remote microprocessor. The question is, can you achieve that latency? Okay, that's the schedulability problem. And I have been going around for 5 years telling people, well, the model's Turing complete. It's got to be undecidable whether you can achieve that latency. So we're going to have approximate techniques. My students prove me wrong. It turns out it's decidable, okay? And the technique they use to prove this is extremely clever in my view. But the schedulability analysis problem, if you can bound the execution times of each of these computations, which of course is individually undecidable, but if you can bound those computations, then the overall schedulability analysis problem becomes decidable. So in conclusion, today, timing emerges from realizations of systems. Tomorrow, I'm convinced timing behavior will be a semantic property of networks, programs, and the models that are used to design systems. Thank you very much.
Time for 2 or 3 questions.
So at the beginning you said that computational systems should reflect what happened in the physical world, and this makes sense. And at the end you said that the world is working on synchronization, distributed synchronization. This also makes sense. The physical world is not synchronized. The only reason for synchronizing it is that computer science, it's easier for us to reason on synchronous systems and to come up with measurements, accurate measurements and predictions. So why don't we work on enhanced methods to actually do what you promoted at the beginning of it?
So excellent question, thanks. Because I think there was let me give you an analogy. Okay, in the world of hardware design, right? Hardware is not synchronous, right? I mean, and in fact, there's been a whole community that has been trying to steer the hardware world away from synchronous digital logic, get free of the clock, right? And there's lots of advantages to it, right? You can actually you can show that you can reduce power consumption, you can get enhanced performance. So why do we stick doggedly to synchronous digital logic? Okay, the reason is that as a mapping technology, as a model, it's extremely powerful, right? It gives us an ability to reason about very complex designs that are much more difficult to reason about with asynchronous logic, okay? So it's because of the value of that mapping technology that we choose that. So we choosing abstractions is always a trade-off, okay? It's a trade-off between faithfulness and the power of the abstraction. And if we say all we care about is faithfulness, then we end up with modeling techniques that are very difficult to use and difficult to analyze because the physical world is messy, okay? If, on the other hand, we care about the power of the modeling techniques and the power of the analysis that we can apply to those models, then we make some compromises on faithfulness. And there's that trade-off. And in my opinion, there's huge advantages in having abstractions that include explicit notions of time in distributed systems. And I've illustrated some of those, for example, in enhancing security. So another really good question, and I think that the issue here, I mean, I get this question a lot when I put this forth, and the argument I think is, the world's non-deterministic. All stuff happens, right? And therefore, we should be really focused on designing systems that adapt to stuff happening that is very unpredictable. And so our goal should be really to make systems that are very adaptive and can kind of observe what's going on around them and self-adjust. And I think that's absolutely true. We do have to design systems that are adaptive and deal with the messiness of the real world. My key point, however, is that we shouldn't ask system designers to deal with non-determinism that is unnecessary. Okay? And in programming, we know this, right? When we write a program that adds two 32-bit integers, we don't feel compelled to check the result in the program. Why? Maybe we should. You know, hardware's messy, right? The real world's messy. We might not get the right answer from that 32-bit addition. But no, you really don't have to check that. It's not an interesting verification problem to, you know, transform programs into something that checks every addition. We've instead, in the hardware, figured out how to make adders and ALUs that are so reliable that despite the messiness of the hardware, they give us the right answer every damn time, right? There's a huge value in that. Let's remove unnecessary non-determinism so that we can focus on the necessary non-determinism and do a better job with it.
So let's thank our speaker one more time.
Thank you.
We now break for 25 minutes and reconvene in 10 seconds.
I'm not sure how to turn this off.
Oh,
It's probably
step
work.
on it.
Right. Crush it.
Crush it. I have no idea.